Mm. Jag vill visa igen vår fantastiska Canvas-sida och kanske i studentvy. Jo, eh, just nu vi befinner oss i vecka 2 av kursen, eller 1,5 för den del. Och inom teori 1 med modulen. I slutet av den här veckan då kommer ni göra en quiz som skulle sammanfatta innehållet av Secure Hash och Symmetric Key Crypto modul som vi pratar om nu och ni läser i kursboken. Så quiz, som Viktor eh, har redan sagt, den är inte öppen ännu, så det kommer att bli tillgänglig att tas från och med klockan 12 imorgon. Ni har hela 3 dagar på er. Vänta nu.
Notering på det. Ja, den skulle öppna sig 22, men den har ändrats till 23 nu för någon anledning.
Ja, precis. Så jag har modifierat det till 23, men i och för sig jag kan öppna det från 22. Så det kan vi fixa nu på en gång. Men egentligen så ni kommer ha bara en försök. Och som jag har berättat tidigare, så eftersom det finns frågor som jag kommer att titta på manuellt, så det finns ingen mening att göra det 2 gånger. Så istället om det händer så att ni misslyckas med första försöket, då i slutet av kursen, just sista 2 dagar, ni kommer få möjlighet att göra om alla eller de quizzer som ni hade otur med. Men som sagt, jag kan ändra. Så själv tycker jag det räcker att ni har ehm, 2 dagar på er, 23, 24 och 25. Ja, jag hör inte vad du säger. Kan du säga? Okej, tyvärr det hörs väldigt dåligt. Så kan du säga en gång till eller skriva i chatt?
Det
Så
var nog tvn i hans bakgrund som lät, inte han.
Okej, så det är ingen fråga som... Okej, det lät som en fråga. Ehm,
Jag har dock en fråga.
Ja.
Boken är ganska bra upplägg det här med under man kan definiera som learning objectives och sen key terms.
Mhm.
Om man är väl insatt i dess nyckelord och det learning objectives då med varje kapitel, har man då en bra överblick med vad quizen kommer att handla om och kommande delar?
Ja, precis. Plus de tema eller fokusområden som vi tar om på lektionerna. Så det är Secure Hash och Symmetric i krypto.
Okej.
Jag kan tipsa er att just första quizen kommer att handla just om hashes och symmetrisk key kryptografiska algoritmer. Och i quiz 2 som blir om 3 veckor nu. Då kommer ni ha en del med true, false eller multiple choice frågor om terminologi för hela modulen. Rent logistiskt kommer ni ha 1 timme på er att göra quizet, men jag uppskattar att det skulle ta mindre tid än det. Kanske 1,5 timme max. Men vi får se hur det funkar för er. Så jag skulle uppskatta er feedback. Mera frågor om quizet?
21 points to get it completed. Approved, godkänt.
Nej, på hela, på alla quizar, ni måste samla på er hälften av poäng. Så på alla quizar. Så nu ska vi se. Totalt, jag skrev om det där på Discord. Ja. Doktorander, vars... Här. Mhm. Det var... Men jag minns att det var... jag skrev om det där. Så det... hur som helst, okej, så vi behöver inte tappa tid här. Men ni behöver samla på er hälften av totalpoäng för alla quizar. Så att bli godkända på quizdelen. Okej. Yes. Ja. Men jag tror jag ska inte ändra på öppningstider. Så 23:00 så det är väl det är väl idag. Så i natt va? Nej, vänta nu. Imorgon. Så efter midnatt ska det öppnas. 23:00, 24. Just det. Och det är midnatt till 25. Så ni måste vara klara under fredag med quizet. Har vi en ny Discord för denna kurs? Ja, jag vet inte, så om ni har använt er utav Discord tidigare, men varje lärare kanske har egen Discord. Nej, men, och just den Discord som gäller i den här kursen, den är länkat här. Okej.
En fråga till.
Ja, absolut.
En check på där du sa att quizet måste vara klart på fredag, men deadline är lördag midnatt. Om man vill kan man göra det på lördagen om man, eller
Vänta, det kanske är jag som har överkomplicerat saker. Jag tänkte, men det är 00. Det är lördag.
Jaha, det var lördag 00. Ja, då förstår jag. Jag tror det var lördag 23.
Nej, så det är fram till midnatt på fredag.
Okej, yes, då är det kristallklart.
Så jag tänkte inte sätta någon deadline på helgen, så det är inte rätt tycker jag. Så det är anledningen. Hoppas det funkar. Så med andra ord, ni har 2 hela arbetsdagar att göra enkelförsök på quizet. Så 1 timme max och förhoppningsvis ni ska klara med det under kortare tid. Yes, men tillbaka till kursmaterialet. So today we will be talking about symmetric key cryptography, also synonymously called secret key cryptography or encryption decryption. And so let me just kill all this. First and foremost, being able to communicate information in a secure way so that only authorized people could get an access to it, can read it. It's I mean, this need exists since ages. So first schemes to write in secret, and actually, I mean, as you all know, the word itself, cryptography, is translated from Greek as writing in secret. Um, so it dates back um, uh, to very ancient times. And first and simple encryption techniques are called substitution ciphers. Since the very first attempts, the algorithms have developed dramatically, as you can say, and now we have two large classes of cryptographic algorithms. The first class, and this is the topic of today's lecture, is a secret key encryption algorithm, and the second big class is a public key encryption algorithms. The difference between the two is that in the secret key encryption, you use the same key to encrypt and decrypt information. So to and in the second class, you have a pair of keys. So you have two tokens. One you use for encrypting the information, and another one you use for decrypting and decrypting information. And by the way, so I see now also a question in chat. I did upload the first class on YouTube. Is it only you, Karsten, who cannot access it, or others also experience problems? Let me see.
I've not been able to open the file in Canvas, but I didn't know it was uploaded to YouTube.
Yeah, I mean, there is a caveat here. So what you need to do, let me see here. So video recording. So what you need to do, you need to open it in a new tab or a new window, and then it works. So it doesn't. All right, it's 3 p.m. So we start our class. Yes. So basically, it doesn't start automatically within Canvas.
Okay, so it's not embedded. Okay.
No. Canvas doesn't support it, unfortunately. Sorry for kind of jumping back and forth. I just thought that it's an important question to answer. So today we will be focusing on secret key encryption. And the basic encryption technique is a so-called substitution cipher. And in this cipher, so you take the original information, the information that you want to protect, which otherwise is also called plain text, and you change the letters of the or change the characters of the original alphabet to characters of a secret alphabet. And so the secret alphabet needs to be kept, or the mapping between the two alphabets need to be kept in secret, and this becomes the encryption key. And the units on which such algorithms work, they can be, well, as you can imagine, single letters, or you can think about substituting any other pattern of letters, like 2 letters, 3 letters, or blocks of code. Yes. And in this class, there are two variants of the substitution ciphers. The first variant is a so-called monoalphabetic cipher. So in this case, you have a substitution pattern which is valid for encoding of the entire message. And the second variant is a polyalphabetic cipher where you have different substitution patterns to be applied for different portions of the original message. Right. Then another technique what is used for as a simple cipher is a permutation. So you basically create a pattern on how you change of changing the position of the letters within the original text. And keeping this pattern in secret is again, so this permutation pattern becomes your key, encryption key. So what can we say about these simple ciphers? First of all, I mean, this kind of encryption you can do with very simple commands. I mean, this you can try yourself in Linux prompt. I mean, there are corresponding commands in Windows for a substitution. So you define the original alphabet, the substitution alphabet, and then you basically supply the plain text, the input message, and this command then produces the ciphertext. So there is not much of an algorithm here. What are the possible problems with substitution ciphers? Well, the substitution ciphers, the main problem with them is the frequency analysis attacks. So it is pretty much straightforward to break monoalphabetic ciphers before all by knowing the distribution of the characters in the original message. So the statistics of appearance of the letters and combinations of the of letters, and this statistics is known for all human languages. So what you essentially do, so I mean, the idea is demonstrated on this slide. So basic statistic analysis of text written in, say, English language can be displayed as a histogram of frequencies of appearance of different letters. And then what you can do, so you can take a ciphertext and perform the same kind of analysis. And then by looking at the frequency of appearance of letters in the ciphertext, you can guess what is the corresponding letter of the original text. So you can get more insight into the statistics of or into the nature of the original language by looking at combinations on the frequency of combination of letters. For example, bigrams or trigrams statistics of appearance. So all in all, so this hints us on how to develop programs that break a code which is created using a substitutional cipher algorithm. So, what are the practical problems with the substitution cipher? The problem is that it works okay for small. I mean, when you change the substitution pattern often. And this becomes impractical in terms of communicating the key. So you need to communicate. The length of the key would be the size of the alphabet multiplied by the number of times you change it for the encoding of the message. And this is very impractical. So in practice, so modern symmetric key crypto algorithms, they use a combination of operations. So they use a substitution operation, but also they permute the position of the symbols or characters in the input text. And here we enter a large class of so-called block ciphers. So ciphers which work, which take a block of original message, a block of the plain text, and encode it one after another. So, pretty much similarly to what we discussed yesterday about secure hashes. So you take your original message, you split it into blocks of a sufficiently long size. And sufficiently long should be from the point of view of performing a brute force attack. So the number of combinations should be very large. And you build your encryption algorithm based on substitution and permutation operations. One of the first algorithms of this kind is called Data Encryption Standard, which is acronymized as DES. And it was, as I said, a first encryption scheme, strong at that time, and it uses block size of 64 bits. So basically, the whole message is split into chunks of 64 bits, and then 64-bit keys are used for encrypting each block. So it was invented back in 1977, and at that time, so based on the computational power of the computers, so it was very hard to break. So nowadays, 64-bit keys are considered to be very small and vulnerable to brute force attacks. So you can basically search the entire 64-bit space in very small time. To fix the problem with the key size, a variant of algorithm was proposed, which is called triple DES, and this triple DES is applying the base algorithm, the DES algorithm, in sequence. So you first, you take a block of 64 bits, and then your target key size is now increasing to 128 bits, and you split the key in two parts, and basically you perform a sequence of encryption and decryption operation with different half of the 128-bit keys. What I want to show you now, I want to just sketch very briefly the idea behind DES algorithm, so DES encryption round. And this is to give you an idea to how these different permutation and substitution operations coexist for encryption purposes. So let me start. So a brief, oops. Brief description of DES functionality. As I said, so the input to the algorithm is message of certain size, L, which is again split into blocks of fixed size. And in DES, so these blocks are 64 bit long. So in addition to splitting the initial message into blocks, you create or you need to agree with your counterpart upon the key value. 64-bit key. So what is happening in DAS is that you take a 64-bit input, and do several rounds of encryption. So you do some initial permutation. So basically, you have predefined permutation pattern. So you take each bit and put it on a different position. And this is reversible. So basically, the decryption goes in the opposite direction. So then you take the permuted block and pass it to DAS round And the DES round, so you need to supply you need to supply a special key, a round key. So this is a round key. And you do the encryption. I will now sketch what is inside this round, and then you pass the result to yet another encryption round. So you perform similar operations several times, actually 16 times, all with different keys. So 16 rounds. Key 16. And these are round keys. And round keys, and again, so there is no stress to remember exact procedure. So all these details you can find in standard description or in the textbooks. But so all these keys, they are derived from the initial 64-bit so-called master key. So you derive round keys K1, K16, which you use for do one round of encryption. And the procedure for deriving these round keys, so they involve well, different random permutation of the original patterns. And now, if you look inside a DAS round, and then what you see, so you take this 64-bit block, and you split it into number 8 pieces of 8-bit blocks. Please give me a second. I think I give you a wrong information here. That goes from a different algorithm. But good that I discovered it. So what is happening here? So there is a splitting involved anyway. So 64-bit block. You split into two 32-bit block parts. 32-bit block. So which is called well, let's denote it as left, and correspondingly a right part bit block right, and then you pass this block through a special substitution function. I will not go into details of it. So basically, there is a pattern on how you substitute pieces of this 32-bit block with secret alphabet. But the important thing is that you, in addition to this, you do permutation. So you take the unsubstituted right block, and it becomes a new left block. 2-bit left block. And you take this substituted part and you add. So this is or you XOR it. You XOR it with the previously the original left part, 32-bit left part of the block. And using this operation, so you get the new 32-bit right part. And these two guys now are combined into 64-bit output. Okay. So again, so this is a very, very high level sketch. Just to show you what is going on. So a block-based secret key encryption algorithm is built using two operations: permutation and substitution. And this is done for efficiency purposes. So the substitution part is very small. So it works on on chunks of very small size. It's even smaller than 32 bits. Actually, it works on add a new block, new data block to it. It will result obviously in a can you say again? Was it a question or just a comment? And I will answer about the AES question now. Absolutely. Well, yeah. Let me just review what I have drawn here so far. So the basic idea of all, I would say, of a general class block-based ciphers is about splitting the message into blocks of smaller size, and normally the size of the block corresponds to the size of the key. And by the way, so the modern encryption techniques like AES, so they work with larger key lengths. So for example, so as you correctly pointed out in the chat, so typical or valid lengths for the keys in modern encryption schemes are 128 or 256. But the principle is pretty much same. So I'm just outlining it on a simplest algorithm of the kind. So you take a 64-bit block and you transform it into another 64-bit block in a predictable manner using the keys. So the difference between DAS and AES is here. So how the substitution is performed and how the keys are generated. But otherwise, what we get is that we get a sequence of 60 sequence of the fixed-sized blocks of cryptotext, of a ciphertext. So in all modern applications, we most likely, you have seen, you have seen it in different use cases when you, amongst others, when you configure encryption for your VPN or Wi-Fi. So you see encryptions like AES, which stands for Advanced Encryption Standard. As I said, the functionality is pretty much similar to DES, but it is stronger, stronger encryption against brute force attacks. But this is only part of the story. Now we come to a very interesting case with block ciphers, is how you can apply it to large portions or large blocks of information. So the idea that I outlined here, that you split your message into a sequence of blocks and then you encrypt it one by one. This is the simplest scheme of how to use symmetric key encryption. Apparently, there are other so-called encryption modes that I will overview now, which basically have different security properties. And I want to review the most representative cases, not everything what is written here, and discuss possible vulnerabilities in each of them. So the very first encryption mode is called electronic codebook, or ECB. So this is the type of encryption I demonstrated. I used when demonstrating or sketching functionality of DES algorithm. It means that you take each block and you encode it independently. And then on the decryption side, you take the ciphertext and you apply the algorithm in the reverse manner to derive or to compute the plain text. So can you think about possible shortcomings of this encryption technique? Any ideas are welcome to the chat, or you can unmute yourself and speak up. So to hint you, I want to show you this example. So what can you observe here? So on the left, you see the original information, so the input, and on the right, you see the encrypted message using the ECB encryption mode. And by the way, you will try this yourself during the practice session next week in this experiment. So what you can observe, obviously, here is that the encrypted message, this is a special case, so obviously, so which can be illustrated only, for the case of encrypting images. So what you do here, so you take the image, you encrypt it, but then you, to display the encrypted image, you treat each ciphertext block also as pixels. So you add a header, appropriate header, so that your software understands that it is a proper picture, and then you can display it. So what you see here is that the encrypted variant repeats the structure of the original text. So if you look, if you would look at the actual values of bytes in the encrypted text and the decrypted and the original text, obviously these two will be different. But what you see here is that you can analyze the encrypted text and observe the regularities. And this is because the original, because the electronic code book encryption treated all the blocks of the image independently. Yeah, this is correct observation. But what is important in this observation that this vulnerability is valid only for the cases where you have some regularities in the original text. The with encryption and cryptography in general, so there is always a trade-off between computational cost and the security. So one of the advantages of this scheme is that it can be performed, it can be parallelized. So you can implement a hardware encryption which work very fast. But if your original, so the if your plain text contains regularities, then these irregularities will be also observed in the ciphertext as well. So now we need to do something about it, and to well, at home, when studying this PDF, so you will see all these diagrams. So now I will skip the actual diagrams and rather come to a point where I want to demonstrate different options on a simpler example. No, the answer to your Amar question is no. The key is the same. So the key is always the same. So you don't change the key for encrypting different blocks. So to demonstrate different encryption modes, so I want to simplify a little bit the encryption algorithm. So now instead of DES, I mean this kind of complicated substitution plus permutation cycle, we will use simple substitution cipher which work on blocks of 4 bits. And so let this substitution be specified in this table. So this is your key, the mapping. So the input block will be mapped to the output block. Also, in what follows, I assume that so we will use, when needed, we will use an initialization vector, and it will be its value will be this 1101. And the plain text that we want to encode is this one. So you see the repeated pattern in the plain text. So it's 1011, 1011, and so we have 3 blocks of 4 bits with repeating patterns in the as a plain text. So first, let me see. I want to reduce this. Something the table we need. And we need something to write on here. So our plain text is 1, 0, 1, 1. 1, 0, 1, 1, 1, 0, 1, 1. And the initialization vector when needed. Well, actually here we in the ECB we don't need it. So ECB. So C substitution table. In PDF in the lecture notes. ECB, electronic codebook. So this one is easy, as I said. So we take the plain text, we split it into blocks of 4 bits, and we encrypt each block one by one. So so that will be denoted as PT1, PT2, and PT3. So you take PT1, you input it into our encryption block, and you will produce a ciphertext 1. So so independently you take PT2, you input it into our encryption block and produce CT2, and the same goes for PT3. Encryption CT3. So, and in our case, so we look up what we have input pattern. So it's number 12. So we change it to this output pattern. So it will be 0, 1, 1, 0, 1, 0. 1, 0, 1, 0, 1, 0, 1, 0. So exactly as I demonstrated on that, I illustrated with a bar graph previously. So what do we see here? We see the repeating pattern. So that's what, and this is bad from the security perspective. However, if our plain text would be wouldn't have the structure, so maybe. Well, even textual documents, they don't have clear structure, immediate structure. Then I mean, it would be a way harder task to spot the repeating patterns. Images also. Tabular information. So if you would encrypt tables, so all the cases with some inherent structure so is vulnerable to this kind of analysis, pattern analysis attacks. But what do we have as options? So the simplest option would be an encryption mode, which is called cipher block chain. So cipher block chaining or chain, or CBC for short. So its principle is quite simple. So you take PT1, and here we need some initialization stuff. So you take an initialization vector and you do XOR. You remember exclusive OR with CBC with the plain text block, and you input the results to to our encryption module, and which will produce a ciphertext 1. However, so this the same block would now go as the new initialization vector to be XORed with the plain text 2. So here again, CT2, and same goes for the very last block. So PT3. You encrypt to get CT3. So what do we see? So we chain. So we change the initialization vector. So and by this we break the pattern. So just to start calculations. So you take PT1 XOR with IV, and so you remember. So this PTI is 1011, and IV is what? Yes, now we need this information. IV, let's have it.
On the PDF.
Yes, 1101. Yes, that's it. So this results in the following. So 0, 1, 1, 0. So when you encrypt 0, 1, 1, 0, you get so from 0, 1, 1, 0. So you get 3 zeros, 1. Right? So and this becomes your first ciphertext block, and the input to next XOR. So you take PT2 XOR 0001, and this becomes 0101. Right, and you encrypt it 010, and so again we look up in the table 1010. It maps to 0110, and this becomes your next ciphertext block. So I will skip the last step, just saying that CT3 equals to 1011. So now your ciphertext message under cipher block chaining is like this. So it's 0001, 0110, 1011. So even though the original text, the input text, contained repeating patterns, so using the same block cipher, operating with the same key, but in a serialized manner, we break these patterns in the output. Yes, where did IV come from? Well, here, as you see, I mean, so this is part of the algorithm. So in this case, so when you want to use this kind of chaining functionality, so you need to do you need to make first operation with something, and so normally, and then you need to introduce this as an extra information. So IV needs to be communicated in clear text. So it is part of the key material exchange process. So you need to agree upon the keys, and you need to communicate your IV. and and IVs they also have to be changed. So we will see an example of refreshing these materials. I mean this encryption encryption material in network protocols like secure socket layer function when talking about secure socket layer functionality. But here we come to another problem. So now let me zoom in into this very first stage and assume that first of all we know that most likely IVs should change because why do we need to change it? Because we want even to avoid situation where the same plain text produces same output. So we want to avoid any regularities in the output of the cryptographic algorithms, and then it is obvious decision to for every encryption act. So for new so for example, when you encrypt a new piece of information, you would use a different IV or you change it regularly when encrypting, for example, a long-lasting communication, so in time. But here we come to a very important fact about IV, sorry. That IV, so you need to refresh it, but it shouldn't be predictable. Or it must not be predictable. Be predictable. What do I mean by this? So when you come to a need to change something, then you need to think about procedure on how you change it. I mean, there are different options here. So you can think that so to generate new IV, you simply add +1 or some constant to the old one. Sometimes it works. So that's maybe not totally a wrong idea to have it. Or what you can do, you can take a message. You can compute a message digest of IV previous to compute IV next. So there are different ways, or you can generate randomly. So as I said, in certain cases, so this way of generating IVs work fine, but in some cases it may lead to vulnerabilities. And this cipher block chaining mode, encryption mode, is an example of the encryption approach which has this vulnerability. So to demonstrate this, let's consider this single cycle of encryption. So you have your plain text, you XOR, so this is XOR, with IV, and you inputted it to encryption, and it produces a ciphertext. And again, so it's a little bit made up example, of course, but assume that you have a black box where you use this encryption to communicate orders about buying or selling stocks. So your plain text messages, they can be, say, buy or sell. So this is your plain text. And when talking about confidentiality services, so I mean, it's valid to assume that ciphertext is observable. So ciphertext is observable. And again, so in this very kind of toy example of attack, so you the set of messages that in principle can be communicated. And you also know that IVs are changing every time so this machine performs an encryption of a text. So next time it changes. But now, so I just want to use this example to demonstrate what happens if this IV is predictable. So, for example, assume I want to know what order was created by a person just before me, using this machine before me. So I take so take ciphertext 1, and I want to try to guess what was the message used, the original message, the plain text message used to produce this ciphertext. Yeah, I cannot reverse the I cannot reverse it because I don't know the previous initialization vector. But for example, because the initialization vector could be created by say digest algorithm. But I can so the only thing I know I know the previous one and the one before, and possibly yes. And now my task is to guess what was the plain text message to produce this ciphertext block. What I do, I can make a guess. So, for example, on one of the alternatives, for example, assume PET was cell. So I construct a message, my message, using the following routine. So I take the previous IV, I XOR it with the current IV, or the one that I can predict that it will be this value, and I XOR it with my guess. PET. And I input it to this block. So what is happening now, so according to the procedure, so this thing I put in here. So what is happening is that this first operation in the cipher blockchain mode, it will cancel out the current IV, which make it exactly the message which was supplied by the previous person. So you don't know it, but you have your guess, and you have the knowledge about the pattern in the IV generation. And then passing through this machinery, so your ciphertext, if your guess was correct, so the ciphertext will be identical. And again, so this made up example of ciphertext analysis attack demonstrates the need that when you refresh the IVs, so they need to be done in an unpredictable manner. I have questions on that. So let me check the clocks. Okay. Finally, I want you to to present another scheme, which is called output feedback. No, sorry, cipher feedback mode. And in cipher feedback mode, what you do, so you start with IV, you pass it to your encryption engine, and then you take plain text and XOR with the result to produce ciphertext. So then you take this result as well, and you use it instead of a new IV as a new IV. So you take PT2, XOR it, and produce CT2. The same goes here. CT3. So CT3. Just to train on this scheme, so I can sketch you the result of the computation, so you can try it at home. So it's again, so your IV is 1101, and the resulting ciphertext, what you should get is 000000001 0001. So this is the ciphertext for our repeating pattern. Which was 1011101110. So basically, each and every encryption mode has pros and cons. They also are vulnerable to certain attacks, but they also have positive moments. For example, the cipher feedback mode and all other similar chaining cipher feedback modes. So they can be used to compute to compute digest of the message. So for checking the integrity of the message. The final thing I want to tell you is, so now returning back to the slides, is a combination of integrity and confidentiality services. So here we have an example of a case where we want to encrypt the data and at the same time protect the encrypted message with the authentication code with the digest. So one possible scheme, well, there are different ones, but one possible scheme is displayed here. So what you see, this is very similar. Well, let me see. So first of all, we have a streaming cipher here. So the difference from what I displayed you previously is that we have initialization vectors that change for each block. So here on top of the slide. So and they go through the encryption mechanism, and so the result of the encryption is used to XOR with the plain text. So what is happening here? You, in addition to the main encryption procedure, which produce the ciphertext blocks, you also use this result to produce the digest in the parallel execution thread. I actually was thinking to finish at this moment. So if you can give me another 5 minutes or even less, then I will finish today's class. Yes. So all in all, what is important to take away in this module? So we talk about symmetric key encryption algorithms. So most of them are based on the approach which is called block ciphers. So it means that you take a message, you split it into blocks, and then you pass the blocks through the encryption algorithm. And the important the important concept to understand here is that you can apply the encryption technique in different orders. And the very straightforward approach is to use the encryption techniques independently on each block. So this is the simplest technique. However, this technique preserves the internal structure of the encrypted document. So to mitigate the possible cryptotext analysis attacks, to discover these repeating patterns, so there are other encryption modes which mix in the ciphertext obtained from each block into the ciphertext obtained for the next block. And there are different variants of it. So most of them are outlined in this PDF, and I also sketched an example for some of them. in my handwritten notes. Finally, so symmetric key cryptography can be used for providing integrity protection or a combination of confidentiality service and integrity protection. So at this moment, I want to finish and maybe ask if you have any questions. So let me at least stop recording. So let's see if you have any questions here. If there are no questions, then please read the suggested chapters in the book, review the slides, and good luck on the first quiz. So basically, yeah, again, in the quiz, I can hint you that there can be a similar exercise on trying to encrypt a given plain text. For this exercise, so stick to the schemes described here in the PowerPoint in the PDF for the lecture notes. So thank you for today. And if you have any questions, so I'm always available on Discord for you. Bye.